When we say a person knows something, we imply a rich, complex state of understanding. We mean they can recall a fact, explain a concept, and apply that knowledge flexibly in new situations. Human knowledge is deeply intertwined with experience, consciousness, and a web of interconnected ideas about the world. But what does it mean when we say a machine, like an artificial intelligence, knows something? Does it know that a cat is a cat in the same way a child does? The answer is both simpler and more complicated. For an AI, knowing is not about conscious awareness or subjective experience. Instead, it is about storing and processing information in a way that allows it to perform a specific task successfully, like identifying an image or translating a sentence. An AI's knowledge is fundamentally mathematical. It is encoded in the numerical values of its internal parameters, often millions or even billions of them, which have been meticulously adjusted during a process called training. Think of these parameters as a vast network of interconnected dials. When the AI is shown a picture of a cat, the visual data is converted into numbers. These numbers flow through the network, and the settings of the dials transform the input into an output. In this case, the label cat with a certain probability score. The machine knows it's a cat because its internal configuration has been optimized to produce this correct label whenever it encounters similar patterns of pixels. This form of knowledge is powerful, but also brittle. It is tied directly to the data it was trained on and the task it was designed for. This distinction is crucial because it highlights the profound difference between biological intelligence and artificial intelligence. A human's knowledge about cats includes sensory details, the softness of their fur, the sound of their purr, their playful behavior, and abstract concepts like their status as pets or predators. An AI's knowledge, on the other hand, is a statistical model of patterns. It has learned that certain combinations of shapes, textures, and colors are highly correlated with the label cat in its training dataset. It doesn't understand what a cat is in any meaningful sense. It only knows how to map specific inputs to specific outputs with a high degree of accuracy, which is a form of knowledge, but a very different one from our own. So, when we talk about AI epistemology, the study of how machines acquire and represent knowledge, we are not delving into the philosophy of consciousness. We are instead exploring the mechanisms by which these systems build predictive models of the world. We are asking how they learn from data, how they generalize that learning to new examples, and how they represent what they have learned within their complex digital architectures. Understanding this process is key to appreciating both the incredible capabilities of modern AI and its inherent limitations. It allows us to move beyond the anthropomorphic language of thinking and understanding to a more precise, technical appreciation of how these fascinating systems actually work. Human beliefs are a messy, beautiful tapestry, woven from logic, emotion, personal history, and social influence. We form beliefs to make sense of the world, to guide our actions, and to connect with others. These beliefs can be firm convictions or tentative hypotheses, and they are constantly being revised in light of new evidence and experiences. A belief that the stove is hot is formed from direct sensory experience, while a belief in a scientific theory comes from trust in established methods and expert consensus. Our beliefs are holistic, meaning they connect to a vast, intricate network of other beliefs about how the world functions. This interconnectedness gives our understanding its depth and flexibility, allowing us to reason about novel situations with common sense. In stark contrast, an AI's belief is a much more sterile and precise concept. It is best understood as a probabilistic estimate. When a weather forecasting AI predicts an 80% chance of rain, that percentage represents its belief or confidence in a specific outcome. This belief is not a feeling or an intuition. It is the direct output of a mathematical calculation based on input data like temperature, humidity, and barometric pressure. The AI system's internal state, its network of weighted parameters, functions as its belief system. This system is tuned to find statistical correlations in data, and its outputs are expressions of those correlations. An AI doesn't believe it will probably rain in the way a person does. It has simply calculated that given the current data, the outcome rain is the most likely one. Another key difference lies in how beliefs are formed and justified. Humans often cling to beliefs for reasons that are not purely rational. We are susceptible to confirmation bias, where we favor information that confirms our existing views, and we are influenced by our social circles and emotional states. An AI, in its purest form, does not have these cognitive biases. Its beliefs are shaped entirely by the data it was trained on, and the algorithm that governs its learning process. If the data is biased, the AI's predictions will be biased, but the machine itself is not motivated to hold a certain belief. It is simply reflecting the patterns it has been shown, making its belief formation process both more transparently logical and more naively literal than our own. Ultimately, comparing human and AI beliefs reveals a fundamental divide between meaning and mathematics. A human believes that a promise should be kept because they understand the social concepts of trust, integrity, and consequence. A large language model might believe the same thing, in the sense that it can generate text stating that promises are important. However, its belief is based on statistical patterns in the vast corpus of human text it has processed. It has learned that the phrase "a promise should be kept" is a common and highly probable sequence of words. It does not grasp the ethical weight behind the statement. Its belief is a reflection of language patterns, not an understanding of human values. No intelligence, whether human or artificial, can learn from a blank slate. To make sense of a complex world from limited information, we all need starting assumptions that guide our learning process. In AI, these built-in assumptions are known as inductive biases. They are the principles embedded in an AI model's architecture that predispose it to learn certain types of patterns over others. These biases are not flaws. They are essential tools that enable an AI to generalize from the specific examples it has seen during training to new, unseen situations. Without inductive biases, an AI looking at a finite set of data would be paralyzed by an infinite number of possible explanations, unable to find a useful pattern. A classic example of an inductive bias can be found in convolutional neural networks, which are widely used for image recognition. These networks are designed with a bias called translation invariance. This means the model assumes that if an object like a cat is important in one part of an image, it will also be important if it appears in another part. The network's architecture uses special filters that scan across the entire image, looking for patterns regardless of their location. This built-in assumption is incredibly powerful because it means the AI doesn't need to be explicitly taught that a cat in the top left corner is the same kind of thing as a cat in the bottom right. The bias helps it learn the concept of cat more efficiently from less data. Another powerful inductive bias is found in models designed to handle sequential data, like text or speech. Recurrent neural networks and transformers, the architecture behind models like GPT-4, are built with a sequential or temporal bias. They are designed to assume that the order of elements matters. When processing the sentence, "the dog chased the cat," the model's architecture is structured to pay attention to the sequence of words, allowing it to understand that the dog is the chaser and the cat is the one being chased. This bias enables the model to capture grammar, context, and long-range dependencies in language, something a model without this bias would struggle to do. It assumes that information flows in a particular order, which is a fundamental truth about language and many other real-world phenomena. Choosing the right inductive bias is a critical part of designing an effective AI system. It's a trade-off. A strong bias can help a model learn very quickly if the assumption matches the problem, but it can hinder learning if the assumption is wrong. For instance, a translation invariance bias is great for identifying objects, but might be bad for a task where an object's location is the most important piece of information. The art of AI engineering often lies in finding the perfect set of assumptions, the right architecture, that aligns with the structure of the real-world problem the AI is meant to solve, giving it a head start in its journey to make sense of the data. Just like humans, AI systems must be able to update their beliefs when they encounter new information. An AI that cannot learn from new data is static and of limited use in a dynamic world. This process of belief updating in AI is a formal and mathematical procedure, a far cry from the often messy way humans change their minds. The core idea is to adjust the AI's internal model to better explain the new data it has seen. This is typically achieved through a process called gradient descent, where the model makes a prediction, compares it to the correct outcome, and then calculates the error. This error is then used to make small, incremental adjustments to the model's internal parameters, nudging its beliefs in a direction that reduces the error for future predictions. A helpful analogy for this process is a hiker trying to find the lowest point in a foggy valley. The hiker can't see the entire landscape, but they can feel the slope of the ground right where they are standing. To get to the bottom, they take a small step in the steepest downward direction. They repeat this process over and over. Feel the slope, take a step, and feel the slope again. In this analogy, the hiker's position is the current state of the AI's parameters, and the elevation is the prediction error. The AI feels the slope, the gradient of the error. and takes a small step, updating its parameters in the direction that promises the greatest reduction in error. This iterative process allows the AI to gradually refine its model of the world, getting closer and closer to a set of beliefs that accurately reflect the patterns in the data. Another powerful framework for thinking about belief updating is Bayesian inference. While not always explicitly used in deep learning, its principles are foundational to AI. The Bayesian approach provides a formal way to combine a prior belief with new evidence to arrive at an updated, posterior belief. Imagine an AI system designed to diagnose a rare disease. It starts with a prior belief that any given patient is unlikely to have the disease. Then it receives new evidence. The patient has a specific symptom. Using Bayes' theorem, the AI can precisely calculate how much this new evidence should shift its belief, resulting in a new posterior probability that the patient has the disease. This provides a principled way for an AI to weigh new information and adjust its confidence levels accordingly. Whether through the iterative nudges of gradient descent or the formal logic of Bayesian updating, the goal is the same: to create a model that learns from experience. When a self-driving car's AI misidentifies a pedestrian, that error can be used to update its model so it performs better in the future. When a spam filter incorrectly flags an important email, user feedback helps it refine its belief about what constitutes spam. This continuous cycle of prediction, error, and correction is the engine of machine learning. It is how an AI moves from a state of naive ignorance to one of sophisticated predictive knowledge, one data point at a time. One of the most significant challenges in artificial intelligence has been its voracious appetite for data. Traditionally, training a state-of-the-art AI model required enormous data sets, sometimes containing millions or even billions of examples. This stands in stark contrast to human learning. A child often needs to see just one or two examples of a zebra to be able to recognize any zebra in the future. In recent years, the field of AI has made remarkable progress in bridging this gap through techniques designed for few-shot learning. These methods aim to create AI systems that can learn new concepts quickly and efficiently from a very small number of examples, sometimes just a handful. This capability is crucial for practical applications where large datasets are unavailable or expensive to collect. One of the most powerful strategies for achieving this is transfer learning. The core idea is to leverage knowledge gained from one task to help with a different but related task. An AI model is first trained on a massive general dataset. For example, a model for image recognition might be trained on millions of images from the internet, learning to recognize a vast array of general features like edges, textures, shapes, and colors. This pre-trained model has already developed a rich, foundational understanding of the visual world. To teach it a new specific task, like identifying different types of rare birds, we don't have to start from scratch. We can take the pre-trained model and simply fine-tune it on a small set of bird images. The model transfers its general visual knowledge to the new problem, allowing it to learn the specific features of the birds with remarkable data efficiency. Another exciting frontier is meta-learning, often described as learning to learn. Instead of training a model to perform a single task, meta-learning trains a model on a wide variety of different learning tasks. The goal is to produce a model that has learned an effective strategy for learning itself. For instance, a meta-learning algorithm could be trained on thousands of small classification problems, each with only a few examples. Through this process, it doesn't just learn to classify one thing. It learns a general recipe for how to quickly build a good classifier when given a new set of categories and a few examples. When faced with a completely new few-shot learning problem, it can apply this learned strategy to master the new task rapidly. These approaches are transforming what is possible with AI. They allow for the rapid customization of powerful models for specialized domains, from medical image analysis where patient data is scarce, to personalized robotics where a robot must learn a new task specific to its environment. By building on prior knowledge through transfer learning, or by explicitly learning the process of adaptation through meta-learning, AI systems are becoming less like rigid single-purpose tools and more like flexible, adaptable learners. This shift brings machine learning a step closer to the remarkable efficiency and versatility that defines human intelligence, enabling AI to tackle a much broader range of real-world problems. The way an AI system represents information internally is fundamental to its capabilities and limitations. This internal representation is the AI's model of the world, its unique way of encoding concepts, relationships, and patterns. It's not stored in plain language or simple database tables, but as a complex configuration of numbers within the model's architecture, often in high-dimensional spaces that are impossible for humans to visualize directly. The quality and structure of this representation determine how well the AI can generalize, reason, and perform its designated task. A good representation captures the essential underlying structure of the data, while a poor one might only memorize superficial details. Consider an AI trained to distinguish between images of different animals. A well-trained model will develop internal representations that are, disentangled, meaning they separate out different conceptual attributes. For instance, one set of neurons might become sensitive to the concept of furriness, while another might encode has 4 legs, and yet another might represent has stripes. When the AI sees a new image of a tiger, it activates the representations for furriness, 4 legs, and stripes, leading to a correct classification. This disentangled representation is powerful because it's compositional. The AI can potentially recognize a new, unseen animal if it shares some of these fundamental features. It has learned the building blocks of animal appearance, not just how to match whole images. The nature of these representations differs dramatically across different types of AI models. In a classic decision tree model, knowledge is represented as a series of explicit if-then rules that are easy for humans to read and understand. For example, a rule might be if a loan applicant's income is greater than $50,000 and their credit score is above 700, then approve the loan. The knowledge is transparent and structured. In a deep neural network, however, the knowledge is distributed across millions of connections in a way that is much more opaque. The concept of a cat isn't stored in one place, but is an emergent pattern of activation across many different layers of the network, making it incredibly difficult to pinpoint exactly how the AI thinks about cats. Understanding these internal knowledge representations is one of the most important and, challenging areas of AI research today. The field of interpretability seeks to develop methods to peer inside the black box of complex models and translate their numerical representations into human understandable concepts. By doing so, we can debug our models more effectively, ensure they are fair and unbiased, and build trust in their decisions. Ultimately, how an AI structures its knowledge internally is what separates a simple pattern matcher from a system that exhibits a more flexible and robust form of intelligence. The quest for better representations is, in many ways, the quest for a deeper, more meaningful form of machine knowledge. Two of the most transformative areas in modern AI, reinforcement learning and large language models, really exemplify distinct but powerful ways of building and using knowledge. Reinforcement learning is all about, learning to make good decisions through trial and error. An RL agent, like an AI playing a video game, or maybe controlling a robot arm, learns by interacting with an environment. It doesn't have a dataset of correct answers to study. Instead, it tries an action, observes the outcome, and receives a reward or a penalty. Its belief system is a policy, a strategy that maps situations to actions, which it constantly updates to maximize the cumulative reward it expects to receive over time. The knowledge in an RL agent is therefore procedural. It's knowledge of how to act. For example, an AI that has mastered the game of chess doesn't necessarily know chess theory in the way a grandmaster could articulate. Instead, it has learned a value function, a belief about how promising each possible board position is, and a policy that tells it which move is most likely to lead to a high-value state. This belief is honed through millions of simulated games. If a particular move leads to a win, a large reward, the AI strengthens its belief that making similar moves in similar situations is a good idea. Its knowledge is dynamic, pragmatic, and entirely geared towards achieving a goal. Large language models, like those behind ChatGPT, acquire and represent knowledge in a completely different way. Their primary task is to predict the next word in a sequence. By training on a colossal amount of text from the internet, books, and other sources, these models build an incredibly detailed statistical model of human language. Their knowledge is embedded in the connections between the artificial neurons in their vast network. This knowledge includes grammar, syntax, facts about the world, and even styles of reasoning and writing. When you ask a large language model a question, it doesn't look up the answer in a database. Instead, it begins generating a response one word at a time, with each new word being its best probabilistic guess for what should come next, based on the patterns it has learned. The beliefs of a large language model are therefore implicit in its ability to generate coherent and contextually appropriate text. It believes that Paris is the capital of France because, In its training data, the phrase "the capital of France is Paris" is an extremely common and high probability pattern. If it encounters new information, say through fine-tuning on a new dataset, its internal weights will adjust to reflect these new statistical realities. This form of knowledge is incredibly broad, but can also be, a bit shallow. The model can state facts and generate sophisticated arguments, but its understanding is grounded in linguistic patterns, not in lived experience or a causal model of the world. This makes it susceptible to generating plausible-sounding falsehoods, or what we call hallucinations. As AI systems become more integrated into high-stakes domains like medicine, finance, and autonomous transportation, a critical question arises: how can we trust their predictions? Knowing that an AI is accurate most of the time is not enough. We also need to know how confident it is in its own judgments, and honestly, why it made a particular decision. This brings us to two crucial concepts: calibration and interpretability. A well-calibrated model is one whose confidence scores actually match its real-world accuracy. If a model says it is 90% confident in a prediction, it should be correct about 90% of the time when it expresses that level of confidence. An uncalibrated model might be highly confident even when it is wrong, making it dangerously unreliable. Calibration is essential for building trust and for safe decision-making. Imagine a diagnostic AI that assists doctors. If the AI flags a medical scan as 99% likely to be malignant, that high confidence level signals to the doctor that the finding requires urgent attention. However, if it flags a scan as 55% likely, it signals uncertainty, prompting the doctor to seek more tests or maybe a second opinion. An AI that is consistently overconfident could lead to unnecessary procedures, while an underconfident one might cause critical issues to be overlooked. Ensuring that an AI's probabilistic beliefs are well calibrated is a key technical challenge, often requiring specific post-training adjustments to align its confidence scores with its actual performance. While calibration tells us if we can trust an AI's confidence, interpretability aims to tell us why we should trust its reasoning. Interpretability, sometimes called explainable AI, refers to the methods used to understand and explain the inner workings of complex models. For simple models like decision trees, this is straightforward. For deep neural networks, the so-called black boxes, it is much harder. Researchers have developed techniques to peek inside these models. Some methods, like saliency maps, highlight which parts of an input, say, which pixels in an image, were most influential in the AI's final decision. This can help reveal if the model is focusing on the right things or relying on spurious correlations. The challenge of interpretability is immense because the language of a neural network is mathematics, not human-like concepts. The distributed nature of its knowledge means there is often no single simple reason for a decision. Instead, the decision emerges from the complex interaction of thousands or even millions of learned features. Despite these difficulties, the pursuit of interpretability is vital. It is necessary for debugging models, ensuring they are fair and not discriminating based on protected attributes, and for providing meaningful recourse when an AI system makes a mistake. Without a window into their reasoning, we are forced to treat AI systems as oracles, whose judgments we can either accept or reject, but never truly understand. Despite their impressive capabilities, AI systems possess a form of knowledge that is often, surprisingly fragile. One of the most significant challenges they face is dealing with situations that differ from their training data, a problem known as out-of-distribution generalization. An AI trained exclusively on images of cats and dogs in household settings might fail spectacularly when asked to identify a dog on a surfboard or a cat in a snowy landscape. Because its knowledge is based on statistical correlations from its training set, it has not learned the robust, abstract concept of dog or cat that a human possesses. It has simply learned the patterns associated with dogs and cats in the context it has seen before. This brittleness can lead to unpredictable and sometimes even dangerous failures when the AI is deployed in the messy, ever-changing real world. Another major hurdle is the problem of noisy or adversarial data. The real world is full of imperfect information. A sensor on a self-driving car might be smudged by rain, or a voice command might be garbled by background noise. While humans are generally adept at filtering out such noise and focusing on the relevant signal, AI systems can be easily confused. Furthermore, they are vulnerable to adversarial examples, inputs that have been intentionally manipulated with tiny, human imperceptible perturbations to cause the model to make a mistake. For instance, Changing a few pixels in an image of a panda can cause a powerful image recognition model to classify it as a gibbon with high confidence. This reveals a fundamental disconnect between the AI's statistical pattern matching and true robust understanding. The very nature of an AI's belief system also presents challenges. Since an AI's knowledge is a probabilistic model, it must contend with uncertainty. Sometimes the available data is simply ambiguous, and there is no single right answer. A well-designed AI should be able to recognize and communicate this uncertainty. However, many models are not designed to do this effectively and can be forced to make a confident prediction even when the evidence is weak. Teaching an AI to know what it doesn't know and to defer to a human expert in cases of high uncertainty is an active and critical area of research. Without this ability, we risk placing undue faith in machines that are making arbitrary guesses in the face of ambiguity. These challenges, brittleness in new situations, vulnerability to noise and malicious attacks, and difficulty in handling ambiguity, all stem from the same root cause. An AI's knowledge is not grounded in a deep causal understanding of the world. It does not know why things are the way they are. It only knows the statistical patterns it has observed. This makes its knowledge powerful for interpolation within the domain of its training data, but weak for extrapolation beyond it. Overcoming this fragility is one of the central goals of next-generation AI research, pushing the field towards models that can build more robust, generalizable, and genuinely intelligent representations of the world. The journey into AI epistemology reveals that for a machine, knowing is a process of mathematical optimization, and believing is an expression of statistical confidence. This form of knowledge, built upon inductive biases and refined through belief updating, has powered incredible breakthroughs. AI systems can now learn from a handful of examples using transfer learning and meta-learning, and they represent what they know in complex, high-dimensional spaces that we are only just beginning to map. From the goal-driven, procedural knowledge of reinforcement learning to the vast, implicit linguistic knowledge of large language models, we have created powerful tools that can reason and predict in ways that were once the exclusive domain of science fiction. However, this exploration also illuminates the profound gap that still exists between artificial and human intelligence. The knowledge held by our most advanced AI is often brittle, susceptible to manipulation, and lacks the grounding in common sense and causal reasoning that underpins human understanding. The black box nature of many state-of-the-art models presents a serious challenge. How can we rely on systems whose reasoning we cannot fully comprehend? The pursuit of more interpretable and well-calibrated models is not just an academic exercise. It is a prerequisite for the safe and ethical deployment of AI in society. We need systems that can not only provide answers, but also explain their reasoning in terms we can understand and trust. As we move forward, the focus must be on developing AI that learns in ways that are more transparent, robust, and aligned with human values. This means designing models with better inductive biases that reflect a deeper understanding of the world's structure. It means creating systems that know their own limits and can signal their uncertainty, inviting human collaboration when faced with ambiguity. It involves pushing beyond mere pattern recognition towards models that can reason about cause and effect, enabling them to generalize more reliably to novel situations and resist being fooled by superficial correlations or adversarial attacks. Ultimately, the quest for AI is not just about building more powerful predictive machines. It is about creating partners in discovery and problem-solving. For this partnership to be successful, it must be built on a foundation of trust, and trust requires understanding. By continuing to delve into the epistemology of our artificial creations, by asking how they know what they know, we are not just improving our technology, we are also holding up a mirror to our own minds, gaining a deeper appreciation for the intricate and wonderful nature of human thought, and charting a course toward a future where human and machine intelligence can work together safely and effectively.